Good afternoon, everyone. I think we can start our lecture. Uh, Today, I would like to talk about, in general, what quantum computing means and what makes, in particular, computing superior to classical computation. We'll go over some of the primitive structures of a quantum computational circuit and some of the early algorithms that started in 1980s and continued to early 1990s. So these early algorithms and the primitives we are going to discuss uh, are going to constitute the basis, of a typical quantum computational algorithm or equivalent to a quantum circuit. So it's important to understand these primitives and early algorithms. Initially, it seems these early algorithms do not have direct practical applications, but later on we'll see many of the constructs that we are going to introduce through these early algorithms will be used as part of more advanced algorithms like the Shor's algorithm and the Grover's algorithm. So to start with, why is quantum computing powerful, and what makes quantum computation in some sense more powerful than a classical computation algorithm? Let's consider a multi-qubit system and let's observe the exponential growth of the basis states. Uh, as we have seen, for a single qubit quantum system, we were able to represent this kind of a single qubit system through this quantum state. Let's say alpha sub 0 cat 0 plus alpha sub 1 cat 1. Now, if you increase the number of qubits to 2 qubits, we have, in this case, a four-dimensional Hilbert space with four basis states. And now these basis states are cat 00, cat 01, cat 10, and cat 11. So in a generic two-qubit system, we are able to represent using these four basis states with complex coefficients alpha 00, alpha sub 01, alpha sub 10, and alpha sub 11. If we add another qubit, let's consider a three-qubit system. Now we have 2 to the n, 2 to the 3 equals 8 basis states, which are cat 000, cat 001, cat 010, cat 100, cat 101, cat 110, and cat 111. So these three basis states, they constitute also a basis for an eight-dimensional Hilbert space. So the dimension of the space increases with the number of qubits exponentially. So in general, if we consider an n-qubit system, we have alpha sub 000, n of them, cat 000, n of them, plus alpha sub 001, cat 001, plus all the combinations of zeros and ones. And eventually we had alpha sub 111, n of them, cat 111. So we have a 2 to the n basis. We can easily see the exponential growth on the number of bases as we increase the number of qubits. If we consider for approximately n equals 0, there are 2 to the 100 bases. So this is a huge number. This is a number that is larger, than the number of particles in the observable universe. So there's no way, you could build a classical computer that would be able to compute all of these 2 to the 100 bases. Even if a single particle, you could build a computer such that a single particle would compute, one of these complex coefficients of one of these basis states, that wouldn't be possible. Today's supercomputers are able to compute or simulate quantum systems up to around 50 or 52 qubits. Above this, above 50, 52 qubits, it's not possible with given the current computational capacity of classical computers to simulate a quantum system. So this is the basic power behind quantum computation. But surprisingly, quantum mechanically, nature computes all these 2 to the n coefficients with a single unitary transformation. Let's consider this diagram. This is a generic quantum algorithm or a quantum circuit. In the input, we have ket psi that we can represent as a linear superposition of all the ket x, all these states that we discussed, all these basis states, so 2 to the n of them, with alpha sub x complex coefficients. A quantum circuit or a quantum computation is simply a unitary transformation of this kind of a quantum state. And as a result, we transform this ket psi state to another quantum state, ket psi prime, but now this time with different beta sub x coefficients. Again, we sum over all the basis states, 2 to the n of them, but now this circuit transforms alpha sub x to beta sub x, a different 2 to the n different complex coefficients. Classically, as we said, this kind of a computation would scale exponentially with n, but quantum mechanically, somehow, for some reasons that we don't understand exactly, nature computes all of these 2 to the n coefficients instantaneously. This is the major reason behind the power of quantum computation. But there's a catch here. There's a disadvantage. The disadvantage is after the computation, let's suppose we obtain a state, new state after the computation, psi prime, we can only measure one of the basis states at a time. Remember, this is a linear superposition of all the ket x. And when we make a measurement, according to the measurement postulate, this state would collapse to one of these basis states with probability magnitude square beta sub x, right? So there's a certain probability distribution. And when we make a measurement, according to that probability distribution, we measure one of the basis states out of all the 2 to the n possible states. So the question is how we can design algorithms that would exploit these unusual properties of quantum systems. In other words, superposition, interference, and entanglement. All of the quantum mechanical, quantum computational algorithms, in order to be able to obtain certain advantage or speed up with respect to the best known classical algorithms, they exploit these properties of superposition, interference, and entanglement. That's not available to classical computation. Okay, let me talk about some important ideas and on quantum computation. How is quantum computation different from classical computation? What are the main or basic features, and some important information about the history of quantum algorithms and computation? So the idea to simulate nature using qubits, in other words, building a quantum computer, was first introduced by Richard Feynman at Caltech in 1982. And his idea was, again, to use the superposition and entanglement properties of quantum systems. And he thought by exploiting these features, one would be able to build quantum computers that could solve problems that's not classically efficiently solvable. Later on, around 1995, Seth Lloyd, now at MIT, he laid out the foundations. He laid out how exactly a combination of multiple qubits can be used to build a quantum computer. Classically, we have seen that this is a hard problem, a hard quote unquote. When we say hard, we mean exponentially scaling, a problem that scales with n exponentially. That's called a hard problem. A problem that scales polynomially or linearly, or in a easier fashion is called an easy problem. So any problem that scales exponentially, we call it a hard problem or a difficult problem. Any problem that scales in polynomial with respect to n, the number of qubits, we call it an easy problem. So we have seen that classically we need to update all these 2 to the n amplitudes at each unitary transform, or each unitary transform. In other words, it is a separate step in the implementation of the algorithm. And a question may rise: can a quantum computer solve any problem that cannot be solved using a classical computer, hard or easy? Any problem can. The answer is no. Undecidable problems in the theory of computation, for instance, the halting problem, it's an undecidable problem. A quantum computer cannot help in that. So if you look at it, both a quantum computer and a classical computer, they need to update all these 2 to the n complex coefficients to compute a unitary transformation. The only difference is the nature does it much faster. Like again, if we consider a classical, an algorithm, if we represent an algorithm, a quantum computer or a unitary transformation, in the input we have this ket psi state, and in the output we have this ket psi prime state. And we said these states are superposition of all the possible basis states of the n qubit quantum system. So the only difference is nature computes these coefficients fast, and classically we cannot compute these coefficients as fast. So one can only compute what is computable classically. So the only thing that we can hope from a classical algorithm, from a quantum algorithm, is some sort of a speed up with respect to a classical algorithm. We can achieve a speed up, but if a problem is not computable, there's no way we can compute using a quantum computer. That's one aspect. Another aspect is, in principle, one can design a 2 to the n by 2 to the n unitary matrix to operate on n qubits. I mean, these operations or algorithms, right? They are actually 2 to the n by 2 to the n unitary matrices on these quantum states. In principle, we can build these unitary matrices using quantum gates, but it has to be an efficient construction. In other words, this construction we should be able to implement using gates that scale polynomially in the number, in number with respect to n. That's what we call an efficient circuit or an efficient quantum algorithm. And we are going to see that in general this is not possible. So for certain unitary operations, we can build efficiently with polynomially scaling number of gates these unitary matrices or these quantum algorithms, but with most of them actually this is not possible. So the algorithms actually are the algorithms that are applicable or efficiently applicable to quantum computation are the unitary operators that we can efficiently actually build the corresponding unitary operator or unitary matrix. Another point is we mentioned quantum computers. They exploit certain properties of quantum systems that are specific to quantum systems alone. They are not available in classical computation. And one of them was interference in a computer. Interference is, as we know, the amplitudes of a quantum system. These alpha sub x that we have seen in a typical quantum system, these alpha sub x, they are complex numbers in general, or in many of the algorithms, we are going to see that they are plus or minus 1. So in order to be able to exploit this interference of these terms, we need to design algorithms in such a way that the algorithm constructively interferes the basis states towards the desired answer. The answer will be typically one of these basis states, because when we make a measurement on the output, a quantum system, we said one of the basis states, ket x. All what this algorithm does is it causes the other basis states to interfere in such a way that, in other words, the magnitudes, the amplitudes, they add up, in such a way that constructively adds up, in such a way that the resulting answer, when we make a measurement, it converges to the actual answer, actual state that we are expecting from the algorithm. This is how we can exploit the interference property in a quantum computer. Another property of quantum systems that's not available in classical systems is an entanglement property. Without an entanglement, an n-qubit system is in a product form. Let's suppose we have these n qubits, and each one of them is can be represented as this quantum state, like alpha 0 ket 0 plus beta 0 ket 1 tensor with alpha 1 ket 0 plus beta 1 ket 1 tensor dot dot dot, and the nth one, the last one, alpha sub n minus 1 ket 0 plus beta sub n minus 1 ket 1. So this is a product state. And this kind of a state scales linearly in n. To represent one of these qubits, all you need to do is to store alpha 0 and beta 0. These alphas and betas, these complex coefficients for each qubit, if you store them, and there are 2n of them, so classically, without having an entanglement, you're not really getting any speed up by using quantum mechanical systems. However, if we again consider a generic entangled n-qubit state, which was ket psi, sum over all the basis states, alpha sub x, ket sub x, 2 to the n amplitudes alpha sub x. As we said, this scales exponentially. So this kind of a, as we discussed, this kind of a state, unitary transforms on these kind of states, is possible to compute quantum mechanically, but not classically, just because there are too many of them. So one needs to use both superposition and entanglement to be able to achieve some speed up or some benefit with respect to classical computation. And as we have seen in the earlier lectures, superposition can be obtained using single qubit unitary operations like the XYZ Pauli operators and Hadamard unitary operators. And entanglement, on the other hand, can be obtained using multi-qubit operations. A typical example was Bell states, right? And we were able to obtain Bell states using an Hadamard and a CNAT, which is a multi-qubit, 2-qubit operator. So we need both single qubit operators and a 2-qubit operator at least to perform quantum computing using the superposition and entanglement property of quantum states. There's a theorem Any unitary operator U can be constructed as a product of a single and two qubit gates. So we are going to see that we can build what we call universal gate sets. In other words, the set of single qubit and two qubit gates that we can that enables us to construct all unitary transforms or Boolean operations. So this theorem says that there is actually a way to construct any unitary operator using only single qubit operators and a two qubit gate. But the problem is this kind of a construction in general is not efficient. In other words, this kind of a construction using single and two qubit gates scale exponentially, in general. So the efficient ones, the ones that scale polynomially, in other words, are the practical algorithms. These are the actual practical algorithms that we can run on a quantum computer. So this is the main trick, behind developing quantum computation algorithms using single qubit and two qubit gates to be able to come up with an efficient quantum circuit using polynomially scaling number of gates to build a corresponding unitary transform. This is the main idea, behind. One of the important gates that we need to consider is the Toffoli gate. It's a 3-qubit gate. The importance of this gate is it is a universal gate in the sense that we can build all available Boolean functions, any mapping from n qubits to n bits to n bits, in other words, any Boolean function, and all unitary operators using Toffoli. Again, this does not guarantee, efficiency of building these quantum computational circuits, but at least according to the theorem we discussed, it is possible. Not necessarily efficiently, but it is possible to construct. A classical AND gate, NAND gate, we know for classical algorithms, it's a universal gate, but it is not. If you look at the truth table of a NAND gate, as we had discussed in the earlier classes, it's not a reversible circuit in itself. But you can, using this construct, you can convert a non-invertible NAND gate through an invertible or unitary circuit in this fashion. This is called a Toffoli gate. A Toffoli gate has 3 inputs, A, B, and C. A and B, these are the control bits. The C is the target bit. So A and B, they are transferred to the output as A and B, but the target bit becomes C exclusive or AB. In other words, AB not. Right? If C equals 1, this actually output is AB not. But if C equals 0, this is AB. So you can obtain an AND gate and a NAND gate depending on the target, the value of the target bit C, whether it's 0 or 1. So in the homework, I'll ask you to show that Toffoli actually acts like a reversible NAND gate by forming the Boolean truth table. So in other words, you consider all the 8 possibilities of the values of A, B, and C. So build a truth table and show that this circuit corresponds to a reversible NAND gate. So we said the importance of Toffoli gate, it's a universal gate. So that means any classical circuit that you build using NAND gates, you can easily convert to a quantum computational algorithm or quantum computational circuit by using a Toffoli gate. Again, this does not guarantee, to construct the circuit efficiently, but at least now we are able to show that any classical circuit can be built using quantum circuits. So let's talk about a little bit the universality in quantum computation. In other words, what kind of properties a universal set of gates must have. First of all, as we discussed, a universal set of gates must be able to generate superposition, because this is an important property of quantum systems, and at least, for instance, an Hadamard gate, right, from a cat 0 state, it can generate a state that is in superposition of cat 0 and cat 1. So this kind of a functionality must be included. Another property is it needs to be able to generate entanglement. Like, as we have seen in the previous classes, using a CNOT gate and a Hadamard gate, right, and a CNOT gate, we are able to generate entanglement. And also, it should be able to produce complex amplitudes, in general, because as we discussed, a generic quantum state like this, right? We have 2 to the n complex amplitudes in general, alpha sub x. But if you don't have a facility or a gate that would be able to manipulate or produce complex numbers, right, that wouldn't be feasible. So an example of this kind of a gate is a phase gate, T gate, which is 1, 0, 0 e to the I theta. Right? This introduces a complex coefficient or a phase in front of a basis state. Some examples of universal gate sets: C naught R pi over 8, in other words, pi over 8 rotation, and then S gate, for instance. S is 1, 0, 0 I. This matrix is called an S gate. This is a universal gate set. There are many of them. You can pick many of them. You can pick a 2-qubit operator and a set of single qubit operators to build a universal set of gates. For instance, the Toffoli gate and Hadamard and S operator, it's also a universal gate. And as we said, you can construct many other sets of universal gates using these operators. Another fundamental question one might ask is, in general, is there an estimate on the number of gates that we need to use to construct a unitary operator U? Solovey and Kitaev theorem answers this question. If you want to construct a unitary operator, U tilde, with some measure close to the operator U, the original desired unitary operator, with an error of, with a precision of epsilon, right? The number of gates that's needed to build, this kind of unitary scales with log 1 over epsilon. Epsilon is the precision, you need to obtain between, you want to obtain between U and U tilde. So the smaller, obviously, desired precision, the larger, number of gates you need to use. Actually, it scales, again over here exponentially, because of this logarithmic, construct. This is an important theorem. It says, at least it says, there is a way with this given scaling, with this given properties, scaling properties, there's a way to construct a unitary operator arbitrarily close to the desired unitary operator. So for a proof of this, you can see the Nielsen and Chang. This is one of the basic texts on quantum information systems, Nielsen and Chang. You can see, check this book for, if you'd like, for a proof of this theorem. But in general, it's a hard problem. Hard meaning, again, exponentially difficult problem to compute circuit complexity. In other words, the number of gates that's needed to build a certain unitary operator is an exponentially difficult problem for an arbitrary unitary transformation. Again, once more, just to be more precise on what is possible with quantum computation, we can ask two fundamental questions. The first question is it possible to simulate classical circuits using quantum circuits? And the second question is it possible to simulate quantum circuits using classical circuits? As we discussed, Toffoli gates, they simulate, an answer to the first question. They simulate NAND gates, that is universal in classical circuits, but also at the same time reversible. So any classical circuit that we can build using NAND gates, we can also translate to quantum circuits using the Toffoli, reversible circuit, as we discussed. Again, the Toffoli circuit is defined as in the input we have control bits cat A and cat B, and in the output sometimes the output the target bit is called the ancilla bit. Sometimes ancilla bit or sometimes answer bit in certain texts, but the output is C plus in modulo 2 A and B. So in other words, if A and B are the same, right? Flip C. If A and B are different, keep the C the same. So this is a controlled CNOT gate, right? I mean, this part of the circuit is a CNOT circuit, but if you add another control bit in the input, right, it becomes a controlled CNOT gate. So C is inverted if A and B equals 1. In other words, A equals B equals 1, else C remains the same. And this is the unitary operator, unitary matrix that corresponds to controlled CNOT and the Toffoli gate. It's since it's a 3-qubit operator, it has to be a 2 to the 3 by 2 to the 3 matrix, right? 8 by 8 matrix. And it is, you have an identity operator in the upper quadrant, and then 0, 0 in the off-diagonal terms, and a CNOT. So, as we said, using Toffoli gate, one can simulate any classical circuit in ON. So it scales linearly with the number of qubits. So just replace each NAND gate with a Toffoli gate. And there are equivalent circuits to Toffoli. If one asks, how we would Toffoli gates in quantum using quantum circuits, this is one construct. Again, you have the two control bits and the target bit. V over here is square root of naught. In other words, V naught, as you know, is the X operator, right? 0, 1, 1, 0, X operator. V is the square root of naught. In other words, if you square this V, V square equals the X operator. So this circuit simulates Toffoli. These are equivalent. So if you want to build this Toffoli in a quantum system using unitary gates, this is the way to construct it. So as homework, I'd like you to show that these two circuits are equivalent. In other words, you consider different possibilities of the control bits, 0, 0, 0, 1, 1, 0, and 1, 1, and show that the output of the circuit is equivalent to a NAND gate, reversible NAND gate, a controlled to CNOT or a Toffoli gate. Okay. The second question we need to clarify, we need to answer is, as we said, can we simulate quantum circuits using classical circuits? We have seen, that this is a computable problem, but not efficiently in general. In other words, it requires exponentially scaling number of gates, and we have discussed the reason for that. There's a theorem actually that explains this. A quantum circuit of size S acting on n qubits can be simulated by a classical circuit with size order S n square 2 to the n. So the most important thing over here is the 2 to the n, because this indicates an exponential scale up. In other words, it's inefficient. It inefficiently scales with n. It uses exponential time and also exponential storage space. I also, before I close the first part, I would like to mention the complexity classes of algorithms that we'll see in quantum and classical computation. There are many of them, but I'll just mention four of the ones that we'll consider. Let's consider all functions, all Boolean functions that maps the strings 0, 1 strings of size n to 0, 1 bit. This is a decision problem because this function is mapping all the 2 to the n possible strings of 0 and 1 to a single bit 0, 1. So this is called the decision problem. Let's consider this problem. We can consider four kinds of complexity classes. P, polynomial time. That means the problem is solvable orders in a polynomial order, n to the k, where k is an integer. So for k an integer, right? This is a n to the k is a polynomial order. So this is called the polynomial time or algorithms or circuits that scale polynomially with n. The other class is, and these are also the easy problems that we have been mentioning about. The other classical complexity class is bounded error probabilistic polynomial time. So these are the problems that can be solved by, again, order n to the k probabilistic circuits this time. The complexity increases polynomially with n, but now considering probabilistic algorithms or probabilistic circuits with error probability less than 1 over 4. So this 1 over 4 may seem to be a large number for an error, but if you run this kind of an algorithm repeatedly, you can reduce this error probability arbitrarily small. So this kind of a complexity class, this kind of a problem is considered to be in the BPP class, bounded error probabilistic polynomial time algorithms. Another class now refers to quantum computations, BQP class. These are the quantum computation algorithms with bounded error and quantum polynomial time. So these are the quantum computation algorithms that scale polynomially in terms of the number of circuits or number of gates that you use to construct the corresponding quantum circuit with, again, with probability of error less than or equal to 1 over 4. This class is called BQP, bounded error quantum polynomial time class of algorithms. The larger class, another class, is the exponential or NP class, of algorithms. These algorithms have exponential time complexity. In other words, the size of the circuit that you need to build scales exponentially with n, order 2 to the n, right? Instead of polynomial, right? If it were n to the 2 or n to the k, right? K an integer, that would be a polynomial time complexity. But if it is order 2 to the n, right, this is an exponential time complexity. So this is the most class of most difficult problems that we considered. Sometimes it is referred to as NP, NP class, and within this NP class also there are other subclasses like NP complete, and others. We'll see some of these algorithms as we go along.